Oi. Ah, agora foi. So we're going to present to you our project. The name of our project is Carcará. For those of you who don't know, Carcará is also known as firehawk. It's a Brazilian bird that lives on dry biomes that have a lot of fires, and it thrives on those environments, so that's where the name idea came from. So for this presentation, we're going to divide it into the three main parts of our project. The first one being the aircraft design. We design our own geometry, so we're going to walk you through that process. Then the fire detection, the algorithm for the fire detection, the sensors and everything else. And finally, the path planning, the trajectories the drones are going to be doing and how they work as a whole. Okay, so starting with the aircraft design. For this part, we kept in mind the requirements of our we wanted to carry as much fire retardant liquid as we could. So that meant we also wanted the smaller empty weight possible because we had a constraint of a maximum MTOM of 5 kilograms. So that means we were looking for an aircraft with a high structural efficiency. We want an aircraft that weighs less, empty weight, and can carry more payload. And when you think about drones in general, I think the first thing that comes to mind is a quadcopter or other rotary wing configurations, but we know that that's not the most effective and efficient in that way structurally. So right off the bat, we wanted to work with a fixed wing configuration because we know it's more structurally efficient. It weighs less and can carry more payload. But the one problem we had was the fact that one of the requirements of the mission was that we must hold position for 5 seconds before the trajectory starts. So that was our challenge, but still we didn't want to sacrifice the whole mission, the rest of the mission, for just a 5-second requirement. So we had to work with that, and we tried to come up with a solution. We did consider some type of VTOL system where we would have the motors and they would switch axis through a hinge joint or something like that. But we figured it would be too complicated for a small drone, and it would also add a lot of structural weight, which was something that we wanted to avoid at all costs. So what we came up with was an innovative concept. The idea is that we have 2 angled motors, symmetrical, and the center of gravity is in the middle of those 2, so in the symmetry axis, one in front of the other. And for a vertical flight, both motors are on tractor mode, so you can see on the image on the left below. The resulting force is going to be vertical, so when it's needed for vertical flight, that's how it is done. And when we wish to, for the rest of the mission, to switch to horizontal flight, the rear motor is going to be switched to pusher mode. And that way, as you can see, the resulting force is going to be horizontal. For this to be possible, we need to be able to change the direction of the rotation of the motor, and to do that, we can use a reversible electronic speed controller. And for this to work well, we need a motor that can produce thrust on both directions. And for that, we chose an electric ducted fan with thin and almost symmetrical blades. And that way, it can produce thrust on both directions. So, yeah. We know that that causes a little bit of a loss of efficiency, that change of direction, so we took that into consideration when choosing the motors and the calculations. For the overall geometry of our aircraft, we chose a blended body wing configuration because it allows enough fuselage space to fit both motors and also the liquid. And also because it allows a more compact aircraft when compared to, for example, an aircraft with a tail. And with that, we can fit more drones in the same cargo compartment. For control and stability, we have two winglets on the blended wing body to help with lateral and directional stability. And for control, we have the elevons and rudders on the winglets. So that was the overall idea, and after that, we moved to the geometry optimization.
So with the geometry configuration we chose, we developed an optimization algorithm to reach the best characteristics for the mission proposed. So to reduce the number of optimization variables, we set some parameters. So we wish the wing to be single section, also with a taper and sweep angle. The motor's position are defined to be as close as possible to the center of gravity, which position is defined by a requirement of minimum longitudinal static margin set by the team. With these definitions, only 4 parameters are needed to parameterize the aircraft. So the wingspan, the elevation section span, the taper, and the sweep angle. During this optimization process, all the aerodynamic calculations are made in a software called SARC Vortex Lattice Method. That is a software developed in our university, which combines the Vortex Lattice Method with airfoil bidimensional data to predict things like parasite drag and the stall of the wing. And also the empty weight estimation was made with some preliminary load calculations considering a carbon fiber reinforced polymer wing, spar box, and the weight of other known components such as the motors, the batteries, the servos, and the sensors. So the objective function of our optimization was based on the empty weight. Once that the maximum takeoff weight was set as 5 kilograms by the competition rules. And we also penalized tip stall for some individuals which show this characteristic. We chose the differential evolution method for the optimization due to the discontinuity of the objective function and also due to its lower susceptibility to local optimal points compared to gradient methods. At the end of the optimization process, we reached this configuration in the cargo space that can fit 30 UAVs within the cargo. For the aerodynamics calculations, the airfoils we choose to analyze, we consider a low or even positive pitching moment coefficient due to the tailless configuration. Also, we kept in mind that a high lift coefficient was needed and was desirable to trim the aircraft in angles of attack near to zero, which is the optimum point of operation of our aircraft. And throughout the project, we found out that the high lift coefficient moment was critical, so we chose the NACA 4312 for the airfoil, for the wing airfoil in all the span, even among other reflector foils used generally in tailless configuration. We calculated the drag polar considering the elevation deflection to trim the aircraft in all the flight envelope. And so for the load calculation, we obtained the VN diagram for the critical conditions according to FAR 23, which is the regulation we found out to use because of the lack of regulations for the category of our UAVs. The body aerodynamic loads were calculated also using a vortex lattice method, considering the loss of lift in the central portion of the wing because of the position of the motors. We also calculated ground loads for different landing conditions. So we made a longitudinal trim analysis to guarantee controllability during all the flight. The static longitudinal stability was calculated considering the variation in the neutral point position during the flight, and the center of gravity was positioned to assured that the minimum static longitudinal margin was at least 2%. The common surfaces were calculated to guarantee the angular velocities needed to make all the maneuvers. Okay, for the performance calculations, we divided the flight in different phases. For the takeoff, we considered two different possibilities. One is the horizontal takeoff and another the vertical takeoff. For the horizontal takeoff, we made the calculations in a 3-degree of freedom model developed by our team, in which we considered the actuation of the elevons when the aircraft reach a velocity higher than the stall velocity, with some safety margin, of course. And we found out that each aircraft needs at least 18 meters of runway distance to take off in this configuration. Also, for the vertical takeoff, the motor choice and configuration were made to assure that it was possible to lift the aircraft in accelerated flight. And to enable this, we angled the motors in 40 degrees in relation to the z-axis. And also, we analyzed the aircraft in another phases, such as cruise, landing, climbing, descent, for the range and endurance calculations. The aircraft structures were designed to resist all the moments and loads calculated, the critical moments and loads. And we designed the spar box to resist all these forces and moments. So the wing surface should resist any load, acting just to transfer the loads to the spar box. So the final geometry we came to was this. Each aircraft has an empty weight of 2.5 kilogram. So we can carry 2.5 kilogram of fire retardant liquid, that is a 160 surplus in the relation to the requirement. Each of them has 2.3 meters of wingspan, and as I have said, 30 drones fit in the cargo arrangement.
So the second main component of our project is the fire detection system. So the first step for that was to choose the sensors we would use. So, we took the challenge to develop all the system considering we have only a monocular camera, because they tend to be much cheaper than thermal cameras and more popular too, what would make it easier to run our system on commercial and popular platforms. The second kind of sensor we need is a localization system, such as a GPS, because our system relies on the drone's position during the time. So this is an overview of our system. So given an input image from the camera, we first locate the fire in the image, and then we use the camera aspects to project the bounding box found to 3D space to finally estimate the fire position in the world. So for the simulation, we develop a feature-based algorithm based on some color masks and morphological operation, which is described by this diagram. So the first step of our algorithm is to remove the ground to isolate the trees in the captured image. And for that, we apply some color masks and morphological operations in HSV space. And this is an example result we achieved. So once we have an image with only the trees, we isolate the firing trees, applying color masks to remove the non-red pixels. And this shows an example of the second part of the algorithm. So once we have the firing trees, it's easy to draw a bounding box that covers all the red pixels found. And once we have this bounding box, we use the camera matrix to project the points in the image to 3D space. But as we use a monocular camera, we lose depth information when the 3D is projected to 2D in the image. So we only have a ray. We don't have a point. So what we do is we take that ray that crosses the image space, crosses the centroid of the bounding box, and we extend this vector using the camera, the drone's position, and the transformation between the drone frame and the camera frame, until it crosses a plane that's parallel to the ground and has a z component of the tree's height, which we assume to be 7 meters in the simulations. So the final estimated fire position is the point where that ray crosses that plane. So we know that in a real scenario, a feature-based algorithm probably wouldn't work very well to general data. So we develop a deep learning approach for a real scenario that has the same input and same output that the feature-based algorithm. So we could just change the black box that calculates locates the fire in the image. And for that we choose the YOLO v5 architecture. So the YOLO v5 is a deep learning architecture that uses the same neural network for classification and localization of the image, and therefore it's very, very well optimized to run on low computational power systems such as embedded systems. And you can check more details on the official website. And this video shows a result we achieved. We download this video from YouTube. We did not record it with our drones. And I'll not show the whole video because it is 3 minutes long, but I can send the link to whoever is interested. And here we see that it detects the fire, even though the drone is very far from the fire, with at least a probability of. So we had some false positives with the maximum of 23% of probability. So we applied the threshold of 30%. So we only consider there is fire when the algorithm detects it with more than 30% probability. And the output are these bounding box. We simply take the larger as input to the projection to 3D space.
Regarding the path planning, we decided on a vector field approach, rather than a moving target, for example, due not only to that being a simple and effective method, but also due to the extensive research from UFMG about the topic. The vector field allows us to focus on the 3D shaped curve we will be following right now, and it also has a proposed article that proposes a control law based on a vector field for a fixed wing. It's with guarantee convergence. It's a simple UVL controller with proportional feed-forward control. You can see the details on the article. The vector field works as the image shows. We have a normal vector and a tangent vector that composes the resulting velocity on the point. There is another article that shows, describes better the algorithm. It proposes the following field, F. The G and H are tuned to a fixed wing vector field following. D is the normal vector and T is the tangent vector. Each drone will go through a sequence of stages. First, by the beginning of the mission, we already have the area to be covered and the number of robots. As such, we can already do the cell division, the cell decomposition of the area to be covered, and proceed each drone to its own cell, respective cell. There is an image from RVs that is to better visualize how the simulation works. We put an area to be covered of 20 meters to better visualize. Each drone is following a green line. Then, once they get to the point of starting the search, they will initialize the path of search. There is also an example of, for 3 drones, how they would follow the path of search in a 20 meter area. More on that later. Then they will, once the fire is found, they will reunite information. That was a requirement from the mission. They will wait 5 seconds information, and the formation was decided to the firefight maneuver. There is an example of firefight for 2 drones, more on that later also. Once the fire is extinguished, they will return to collection in a predefined location in the map. So for the area segmentation, we had to divide the area to be covered in cells for each drone, equal area cells. For that, we decided on a polygonal shaped area for each drone. There is an example for how the algorithm would divide the cell for 2, 3, 4, or 5 drones. Besides that, we have to apply a method for covering the area. We, based on literature, we decided on a lawnmower method, pattern. And besides that, the lawnmower allows for a Bezier curve on the turn so that the fixed wing can perform better the movement. Moreover, there is more than one way to cover each cell with the lawnmower method. We decided to use a line swept decomposition algorithm. There is this article there. To maximize the altitude of its cell, that is the largest dimension of its cell, so that we can avoid having multiple turns. As you can see, dividing the coverage area with that method, we have a lot of turns, and dividing with the maximization of the altitude, we can reduce the number of turns and be more energy and time efficient. There is an example of how it would work for 3 robots. Again, the green circle represents the range of detection, but we reduced it to better visualization of the RVs, but it's customizable for each height of the mission and each drone. And for the targeting maneuver, we prioritizes the optimization of simultaneous area coverage and being adapted for the fire and the size of the fire and the number of robots. That is that when in the vision detection, we calculate the size of the bounding box, and based on that and based on the range of action, that is the range of which we can apply the fire retardant based on the height of the targeting maneuver, we can go with multiple or single lines of drone action. We'll have an image for that. As such as the whole area of interest is covered at all times. We also adapted that for a different height when targeting the fire, as such as we could avoid thermal gusts always as possible and have a smoother curvature, so the drones almost goes approximately in a straight line when targeting the fire. There is an example for a larger range of action. They only need a single line of drones to cover the whole area consistently. For smaller ranges of action, they will need more lines. And as you might have noticed, most of our simulations run with 2 drones. That wasn't due to lack of our algorithms, but due to our computational resources. That when we would use exceeding robots, they would disarm and fail. That actually gave us a range of a problem that might occur in a real situation, real mission, that we needed to guarantee that the whole area would be covered, even though one drone might fail. For that, we found out that the critical points were the starting of the mission, when if any robot fail, they already calculated the cell segmentation so that the area wouldn't be covered, but there is a check for if any drone has disarmed, and if any drone has disarmed, they will recalculate it once they get to the starting point of the search site to guarantee that the whole area is covered. Also, for a similar reason, when I reunited information to perform the firefighting maneuver, they would also do this check and guarantee that the target area will be consistently attacked during the whole operation. That's it. We are open to questions.
Thank you so much for the presentation. There is some suggestion from one of the members of the jury board. You decide, they suggested that all the groups present and then you make the questions afterwards, or do you prefer to make the questions direct to each group after every time? It's up to you. It's better. Okay. As you wish. Okay, good. Go ahead. Which order? There's a good point here for having all the groups presenting, and then we can ask questions. Okay, good. As you wish. Thank you. Okay, thank you. The jury board decided that you can wait for the presentation of all the groups, then they will make the questions for afterwards. Okay, thank you very much. And now I will ask team 2, that's USP Semiar, to take her place here.
Morning, everyone. My name is Guilherme, and today we are here to present the No Fire Squad project from a TINA team. But first, who are we? Who is a TINA team? A TINA team is part of the group CMR, that is a group of robotics and mechatronics from University of São Paulo. Nowadays, we are composed by more than 130 members, divided in several areas. For this competition, our team is composed by me, Guilherme Vilela, Matheus Martins, Lucas Cavalcante, Daniel Miguita, Raul Contrim, and Guilherme Barella. Now, for a short introduction of the team, I invite Guilherme for the microphone.
Morning. I'm going to give you a brief explanation on the team. Even with advanced modern technology, the number of fire incidents is still alarming, and traditional methods can often be too expensive and ineffective, also getting the firefighters in dangerous situations. Imagine the proposed scenario: a forest fire, a large area with multiple focuses of fire, making the detection and neutralization hard for ground-deployed firefighters. That's why our project brings a different approach to fire combat, aiming on both safety, not requiring direct human contact to fire focus, and efficiency, using modern algorithms for fast detection and neutralization.
So, to understand a little more about the problem, we had a meeting with the firefighters from São Carlos Fire Department to understand more a little how the fire works and behaves, and answer some questions that are here. First one, how do firefighters work during a forest fire? So it's a very hard job to stop a fire, and it's also dangerous for the firefighters. So when the fire is out of control, it's nearly too impossible to stop it in an easy way. So the firefighters, they usually do fire breaks to try to limit all the area the fire can burn. This, and eventually the fire will decrease its intensity. The second question is, how the drones can be used during the fire situation? When asked to the firefighters, they said one of the best use for the drones are for prevention and detection of fire when it's before they are out of control. But there's a problem in this situation that the time between the beginning of fire and then when it's get out of control is very short. So this job needs to be very fast and precise. And the last question is, what's the best way drones can be used to really fight a fire? So after the conversation, the group came to conclusion that it's not effective to just dump all the fire retardant liquids on the fire in the middle of the fire. So after detecting the fire, all the drones will be disposed around the fire, and then the liquid will be released to try to simulate what firefighters do, that is the fire breaks. All this procedure will be better explained in the simulation part. So now I'm going to talk about our project, that's No Fire Squad. This drone here in the image is the DJI F450. That's the drone used during our simulation. So all the electrical and mechanical requirements will be focused on this drone. First of all, I'm going to start talking about the electrical components. As said, all the components will be electrical components will be from the drone kit that is recommended by DJI to this drone specifically. But it's important to remember that once the DJI F450 is a very versatile drone, it's possible to change the components during tests in order to evolve it in the future. For autonomy, we have the battery that is equipped. The drone is equipped with a three-cell LiPo battery with 5,000 mAh, and the total weight for the vehicle is nearly to 1.5 kilos with no payload, and adding the payload we have to 2.5 kilos. By the calculations, we had nearly to 13 minutes with no payload of autonomy, and with payload nearly to 6.5. That is, according to the simulations, we have it's correct.
As one of the competition criteria, the design drone should be able to lift, carry, and drop a payload, the fire retardant liquid. To solve this problem, the chosen solution was to use an electromagnet device that can be easily controlled by charging and uncharging it with a current, altering its magnetic properties, making it able to both lift and drop the payload.
Now talking a little about our mechanical part. And the competition have a few requirements that goes from the weight, the volume, and we have a few of our own and one that is within the problem. The first one, it's the takeoff max. As discussed before by Daniel and Guilherme, the drone have approximately 2.5 kilograms. That is much lesser than the maximum of 5 kilograms. The second one, as we've been an university group, we have a very limited arsenal, budget. We have a very limited budget. Then we need to be something that can be replicable in our context. The third one, it's the volume limitation. The drone needs to be under 0.5 cubic meters. And our drone have 0.025 cubic meters. 0.025 cubic meters being attending the requirement. And the last one, it's the fire resistant. The drone will be flying across fire, and higher temperatures would impact the batteries, the electronic components, and this brings us a new requirement. The drone needs to resist to heat and fires. Then we came with the solution of the Aeromid armor. Heavily inspired in the Pharaoh's drone that can outstand in flames as displayed, and it will fly late. We need a drone protected from the heat. We took a heavy inspiration in the Aeromid, but it have a few problems. The first one, it's a little expensive, but it's a vital component for our project. Thus, we'll keep it here. It can protect the battery and the electronic components, but it hasn't been tested by long periods of exposure. So it comes with little problems, but we are studying on this for the development of an Aeromid armor.
Now we're talking about the system that we designed for the project. First, we're going to talk about the software that we used so far. Considering that we need a robot application, the robot operating system ROS was chosen to be our core. With ROS, we're able to use the virtual environment provided by the competition to create a simulation using the gazebo toolbox. And in order to control and manage all aircraft, we chose to use the MRS system, multi-robot system, to deal with these algorithms inside the competition, as well as outside if needed. Next, our approach was the development of a drone swarm. Because of the complexity of our problem, we chose to use a 9-drone swarm, allowing a larger area to patrol and a small time in the fire combat. Additionally, RD relies on the use of a master drone, which is going to have the task to map the fire area and later in the simulation. Using a large group of drones like this, it's good because you can quickly analyze data while you can perform 2D and 3D formation and trajectories as well. Finally, we're going to talk about the swarm itself. Each drone in the swarm presents itself independently, acting as a source of sensor data, capturing images and send its position. All this data is sent to a central node, which presents inside a stationary machine, acting as a master node controlling all the swarm. In that case, the central node could deal with all the data and send to each drone all the information about velocities and trajectories and position inside the formations. And in order to control the state of the operation, a state machine was used to deal with different decisions based on the current state of the mission, presenting, for example, the start of the patrolling after the first formation is reached, or start the fire combat after the fire mapping.
Now you come to know our project. Now we will show you how we work on the proposed mission. The first thing of the proposed mission, it's the aircraft's airdrop. A big problem for us, but we came with idea. The idea is to drop not the drone, but a case to protect the drone connected to a parachute from the KC-390. The parachute would open immediately after leaving the airplane, and the case would start to fall and then open mid-air. And when it opened mid-air, the drone would start a free-fall protocol that some platforms have, as example, the free-fall from Autopilot and others. And we would be addressing a few of the problems, like the air vortex and other problems. And this was inspired by a military application of this nowadays. That's the field dropping of vehicles, and it is used by one of the American military forces, and Brazilian army uses this type of application where they drop vehicles on the field. It needs to be tested for our application. It needs to be more validated, but we have this initial, and with this come our possibilities. The possibilities are not only for the SARC problem. They come for many other problems where we have difficult access to the area. Being able to drop drones from a plane would open many and many possibilities with the case drop.
Okay, so after the airdrop, the swarm needs to start to search for the fire spots. So searching for the fire spots is built upon 3 pillars: patrol strategy, fire detection, and fire mapping. So the goal of the patrol strategy is to find the forest fire autonomously and as fast as possible. So our method was based on divide and conquer. So the swarm is divided to inspect the different areas of the terrain. So once one of the drones finds the fire, it can send a message to the others, and then can fly to the area where the fire was located. Here we have some representation of the trajectory performed by the drones. They are Hamiltonian circuits, because we use this because it's very effective to cover the area, but other patterns of trajectories are also possible. Now we can talk about the fire detection method itself. In a real scenario, it's very challenging to perform an effective fire detection. Some challenges are poor illumination that can be caused by weather conditions or by the position of the sun, for example, and occlusion due to dense vegetation around the fire, and also by the false positives. That is, when there's something that looks like fire but is not fire, like light reflection on metal or water surface. So to face these challenges, our method is also based on visual camera. So we can perform active image segmentation using a UNet CNN. So the camera captures the frames, the image goes through the layers of the CNN, some computations are done, and we can verify if there is or there is not fire in that area. Here we have some of our results of our model. So we have different light conditions. But just this information of if there is or there is not fire in the area is not enough to perform this autonomous firefighting. The swarm needs this 3D information. So the fire mapping task is extract this 3D information from the images. We can estimate the center of fire, for example, and the bounding circle coordinates in respect to the 3D world frame. And we need to provide this 3D data to the swarm formation. So our method is based on sensor fusion. We can integrate the camera. We have some parameters of the image, some parameters of the camera, and we can integrate with the data received from the GPS, especially the Z value, that is the altitude of our drones. And here a representation of these estimations.
Okay, so after the center of the fire's detection is completed, the swarm will advance to the last phase, to the firefighting phase of the simulated mission. It's important to notice that our strategy in the firefighting was inspired by real strategies used in real forest fire situations. And so having this in mind, our approach starts with the swarm creating a circular formation around the fire area. And then the swarm will start a coordinated movement of rotation and reducing the formation radius as it releases the payload. As you can see in the GIF, the swarm spends more time in the peripheral area of the fire, trying to stop the fire from spreading, and then goes to the central part in a faster way. Now analyzing some results of the firefighting strategy, we can have a look at this image in which each dot represents the collected position for the UAVs. And the red area represents the burning area of the fire. Therefore, analyzing this data, we can conclude that the fire strategy could be applied in a real forest fire situation because it covers a good area percentage of the burning area and reduce the risk of the expansion of the fire. Now, after the firefighting phase is done, the swarm will advance to the last phase of the simulated mission, the return to base. Initially, the swarm will need to regroup, create a new formation, and head to base by translating this formation to the base location. After reaching the base position, the swarm will execute a coordinated landing while maintaining the circular formation with a reduced radius to facilitate the collection of the drones after the mission is done. Now, we would like to talk about some conclusions and show the full simulated video and
discuss some improvements, possible improvements in the project. The simulation begins after the drones are dropped from the KC, and each drone is separated in its patrol quadrant. Now, as you can see, the first drone found the fire and called all the others to its position. And now the center drone is gaining altitude to have a better view of the fire area and be able to centralize it more efficiently. We can see the centralization happening in the image in the corner. The drone has found the center, and the firefighting strategy will begin. It's a little hard to see because of the colors of the trees, but the drones are rotating and reducing the formation radius. Then the final phase of firefighting, the drones go to the center and create the new formation to head to base. Now the drones are heading in a circular formation, and will execute a coordinated landing when the base position is reached. I will jump now, but it's only the image that you have saw before in the other slide. Okay, now to discuss some further improvements in the project that we have in mind are simulating mechanical tests of aramid, integrating the visual and thermal cameras to improve the fire detection, implementing a fail-safe mechanism in which could be used in case of a failure in the master drone, so the swarm would be able to adapt to it. And finally, test other drones configurations, like a VTOL or fixed wings, to see what would be best applied in our simulation.
And I would like to thank you all, and the organization, the sponsorships, professors, and everyone that's present here for prestiging our presentation. Thank you.
Okay, we'll take now a coffee break and we'll come back later. Well, welcome back, everyone. We have now the presentation of Federal University of Santa Catarina.
Hi, everyone. My name is Iago Silvestre, and I'm one of the members from the Federal University of Santa Catarina. I would like to present a work that is titled Collaborative. Desculpa. Ah, tá. Desculpa. So let's start again. My name is Iago Silvestre. I'm here to present the work from the Federal University of Santa Catarina that is titled Collaborative BDI Agents Firefighters. So first I would like to present the rest of the team who could not be here with me today. The team was composed basically of 6 members. 4 of them were from Florianópolis and 2 of them from Blumenau. It was composed of 3 students, me, Bruno de Lima, and Pedro Henrique Dias, and 3 professors, Leandro Busbecker, Jami Hubner, and Michael De Brito. We would also like to thank the collaboration with the Robota group, who offered themselves to start the recovery process of the drones from the Provent project, and especially to Mike Cuevas, who is here with us today and helped on the process of recovering the SK-450. So first, I would like to tell the idea of our proposal. Our team has experience from previous projects devoted to the design of an UAV from scratch, which is the Provent project. Is a collaborative effort between the Federal Universities of Santa Catarina and Minas Gerais. On such project, it was developed different works using multi-agent programming. So our efforts here focus more on the embedded software part of the problem for the firefighters. So this involves the actions that need to be performed by each UAV. So in our case, the logic of the agents, and the libraries that translate the desired actions into commands to the aircraft, also allowing reading the aircraft sensors. So we can point out some advantages of our solution. The multi-agent programming is normally simpler to program. It uses high-level programming constructs to implement autonomous, collaborative, and goal-oriented behaviors for the agents. And in our case, it is commanding the UAVs. It is hardware independent, so it can be easily transferred to other types of aircrafts. And it is it offers high scalability. So it is easy to increase the number of UAVs that we deploy on our solution. So let's have an overview of the solution that we proposed. So first, with some changes to the ambient setup script from the SARC environment, we initialized the gazebo simulation. We did some changes for our proposal that we can discuss later, but this is part of the SARC environment. But in addition to that, with the gazebo simulation started, we also programmed JSON BDI agents, and we programmed a fire detection that is programmed in C++. So the JSON BDI agents doesn't directly speak with ROS. So we had to build a JSON ROS interface that converts ROS topics into beliefs of the agents and also provides a way for JSON agents to request ROS services. So these 3 elements combined can give us a simulation that have UAVs being commanded by BDI agents. So let's have a summary after the introduction of what I'm going to talk about later. So first, we're going to talk about the modifications to the SARC environment. This is going to be very brief. And then a little bit about the JSON BDI agents. Shortly about the fire detection, because it's very simple. A little bit about the JSON ROS interface that the Blumenau part of the team developed. We're going to have a demonstration of the simulation. We're going to talk about the roadmap for implementation. And then finally, some conclusions and what we can improve and possibly work on the future after this project. So we can list a little bit about the modifications to SARC environment, but they're rather simple. We added support for 6 UAVs, which we proposed on our solution. We also tested 12, but from the ground instead of falling from the KC, due to space of the cargo. We added a window on the Tmux script responsible for running the ROSBridge server. I'm going to explain why we need the ROSBridge later, but it has to do with the JSON ROS interface. We did some changes to the fall Python script. This script is responsible now for arming and enabling immediate activation for all the 6 UAVs, and some tuning on the resistance to ensure a stable simulation. We also did some minor changes to the SARC low map script, because this is the script where the word file is generated, and we added a placeholder library for spawning an object on top of the detected fire. So yeah, with all that said, let's jump onto the JSON BDI agents. As a team, these agents perform the following steps. Each agent tries to find the fire spots. The area is divided amongst the agents, so the agents, based on their IDs, calculate an area and waypoints inside this area for them to find the fire spots. They extinguish fire, so when one agent finds the spot of fire, it asks for other agents to help extinguish that fire. And once the fire is extinguished, all involved agents goes back to the first step, that is searching the area. And when all area is verified and fire is extinguished, all agents go to their landing point and land. So JSON is an extended version of AgentSpeak, multi-agent programming language. So BDI stands for belief, desire, and intentions. And it is a kind of aspect of the multi-agent programming that establishes that the agents have beliefs, they perceive the world around them. Agents normally don't have the perception of all the world, so they only have the perception of an area around them. They have desires, in other words, they have goals. They aim to achieve something, and they have intentions. So with these desires, they choose a plan to tackle this goal. So we have here an excerpt of the code of the agents, which is only the start. So at the start of the code of the agent, it adds the goal of start. And here we have a plan on how to deal with start, symbolized by the plus, and the exclamation stands for the goal. So here we have a goal added and a plan added on how to deal with this goal. For a start, we only have one plan. At the start of the plan, it prints starts. It adds the goal to calculate its trajectory around the world map. And following that, it adds the goal to follow this trajectory. So the trajectory logic is very simple. We did a base of twos, of multiplications of 2. So with the world map being known, the worlds based on their IDs separate these areas in rectangles, and each drone is responsible for an area inside the world. And inside this area, based on a variable named camera range, the drone calculates a number of waypoints inside this area to perform its waypoints. So here we have a little bit of the agent part that is on how it combats fire. So here is one of the plans. He has another plan for detected fire. So when this agent receives the goal that detected fire is being detected on n, so n is an integer, and here below this plan is the context of the plan. So if my number is n, so if I'm on top of the fire, then it starts combating this fire. So here we have the rest of the context, but it's not really interesting to expand here. So how it deals with the detected fire, it suspends the goal to follow the trajectory. It removes the previous belief that is named status and adds a new one that is the status of combating fire. It prints for debugging purposes that the fire is found by the respective drone. It broadcasts to the other drones that it has found a fire, and it then adds the goal to combat this fire. Here we'll talk shortly about the fire detection C++ extension. It is basically a very simple C++ ROS subscriber and publisher that subscribes to the camera's topics and processes the images that is being published. So it detects pixels with red tonality, and if the red tonality pixels are greater than a threshold, then it publishes on respective topics that it has found fire, and the agents can work with that. So let's talk about the JSON-ROS interface. We developed the JSON-ROS interface that provides a way for JSON BDI agents to request ROS services and read or write on ROS topics. So in essence, the current implementation consists of a JSON-ROS interface that establishes communication between JSON agents and ROS through the WebSocket protocol, and we use ROS Bridge as a transport layer. So this JSON-ROS interface translates the resource of ROS, services, and topics to the agents. The topics become beliefs of the agents, the topics that we declare, of course, and not all topics. And while the repertory of actions of the agents, including service requests or topic writings, are available through our interface. So there's two main files that are responsible for setting up this environment. So the first one is the demo embedded agents ROS. So this file is responsible for setting up which ROS topics are going to be converted into agent beliefs. So yeah, here we have a little bit of the excerpt of the code. So we, for example, we added topics that are being published on odometry, for example, GPS logo odom, and the type of message. And this topic, this ROS topic, now becomes an agent belief. It perceives the word from this topic. And following that, we have the my ROS master Java file, which is responsible for setting up which actions that will perform by the agent and how these actions they work with the ROS topics and ROS services. So here we have an example of the action named goTo, and this goTo is a service request that is requesting the MRS UAV system to go to a determined point. We also have a writing on the writing on a ROS topic. Above that, there is responsible for dropping a placeholder library that we're gonna talk a bit about later. So let's show you the simulation. I'm gonna speed it up a bit because it's a bit slow. 6 minutes. So we start by running the start script. Here we have the initialization of the 6 drones. It's going to wait for odometry, but here we spawn the trees. We spawn the landing point. And with that done, we can unpause the simulation. It starts the ROS gazebo simulation. It's going to start spawning the UAVs inside the KC. And when the drones are spawned, MRS UAV course starts running. So yeah, here the fall Python script starts, and the drop process begins. Here we had a little bit of frame drop. We can skip this part. The drones are falling. I believe during this process, we're going to start running the C++ extension, which is responsible for processing the cameras attached to the bottom of the drones. Yeah, here we have it. We start the C++ extension. The drones are still falling. Yeah, here we can have a top view of the 6 drones falling dropping, right? And hovering over the ground. When this process concludes, we can start running the UAV agents. So yeah, here we have the Java interface of JSON. I'm going to pause because you probably can read here, but each agent is printing the messages that I talked about previously. It is printing that it's starting. It's just printing that it's calculating the landing position, calculating which area it's responsible for. Then it starts calculating the waypoints inside this area. And finally, it starts following the trajectory. So here we speed it up. The drones are going to their designated area. Yeah. Here we can see the drones are moving towards the trajectory. In this case, on this simulation, the drone 6 trajectory ends up flying over the fire. So when the drone achieves this, yeah, here we have it. The drone flies over the fire tree. It broadcasts to the other agents that it has found fire, and the other agents suspend their trajectory to come help. Here we have the inspector for agent 6. It hovers over the fire for a little bit, and then we use the placeholder library to spawn an object to symbolize that it's acting upon the detected fire. So the remaining drones, as I said, pause the trajectory and come help the detected fire. They do the same, they hover over a little bit, and then they spawn an object to symbolize the fire combat. Once all drones combat the fires, after each drone combat the fire, they return to their original trajectory to scout for the area for other possible fires. And here we have the drones that finish the trajectory. They start waiting on the end of the trajectory for all other drones, so they can go together to their landing position. So here we have all drones finished, and they start moving towards their landing point. UAV 1 is the first one that reached the landing points. Once it reaches, it immediately starts the landing process. And the same occurs for all other remaining drones. So yeah, that's the basic overview of our simulation process so far. So, yeah, roadmap for implementation. Currently, we're finalizing the process of reproducing the experiment made by Marcelo Menegol on his master thesis that uses the modified version of Turnig SKE 450. So what Marcelo made was he basically made a framework that JSON talked to the SKE 450. And it was basically a framework that was responsible for taking off the drone, setting up waypoints inside an area, and then landing the drone. What Marcelo Menegol didn't do on his master thesis, it didn't involve ROS. It was basically just directly between JSON and the drone. So we also listed our roadmap includes an improvement of the framework, enabling communication with ROS. So here we can show, since we're not going to have a live demonstration, we're still finalizing the steps of the fine-tuning of our routers and detecting possible problems. We can show what Marcelo Menegol did with the same drone, but not including ROS, just basically direct conversation between JSON and the drone. So here the drone starts the takeoff process. Once it takes off, it starts following a trajectory of 4 waypoints. So here it goes to the first waypoint, to the second one, then to the third, and finally goes to the final waypoint and then starts the landing process. That's it. So with all that said, what we could improve on our work? Actually, I forgot. Let's do a recap of our proposal from the Santa Catarina team. So our proposal basically did some slight modifications to the SARC environment. It programmed JSON BDI agents, and it also programmed a very simple fire detection in C++. But this is all bound to the SARC environment, and it is nice to show as a demo, but it is bound to this area of combating fire. What we produce that could be further used for future is the JSON ROS interface that enables JSON agents to talk directly to ROS through services. And this is an area we are aiming to do future works on this area. So, future works, finalize reproducing Menegol's experiment that we showed here in the video, and improving the framework to enable ROS communication. Improve mission speed and drone stability. The simulation, we had to speed it up to show here, but it's a rather slow simulation. And we also have to refine agents logic to include more multi-agent systems teams, such as auctions to who is going to help combat the fire, because so far the agent logic is rather simple. Here we have a little bit some references and the contact.
Professor, would you like to do the questions now?
I give the floor for the jury board now, if you want to go on. And I would say it's you can give the questions for each group as you want. Yes, yes, please come to the stage here. Oh, okay. Brigadeiro Forador, can you hear us? Is it okay? Okay. Please, I'm right at the side of your computer. Please let me know if you have some questions for the group. We are going to share the floor with other jury boards. Okay. Okay. Oh, thank you.
Okay, so first of all, I'd like to start saying that you've all done a great job given all the time and resources constraints you've given and the complexity of the challenges. So I think it's an amazing job. And please, we will have some questions and comments here, of course, but take that as something for you to take away and from here and learn from that. But all great jobs indeed. So perhaps we should start with one team. So as an overview, I think that the three teams, they have had emphasis on different parts of the problem. And reading the report and also the presentations now, it's clear that each team had a different emphasis on the problem, and the areas that you focused are all critical and important in equal manners. So it's a hard job for us, for the jury. And it's interesting because if you combined all the three, you would have a very whole and complete solution. So it's an interesting thing to mention. So, so for instance, one of the teams focused more on the air vehicle design in a general sense, whereas the other two teams used a COTS solution, a commercial off-the-shelf solution. And one of the teams had a more emphasis on the concept of operation. They are even discussed with real firefighters, how do you do this work, and try to learn from the actual operation. And the other team, on the other hand, had a greater emphasis on implementing the concept of operation through software and thinking really through different conditions and situations. Well, if I have, that's a just general statement. So if we are to ask one question for each group and go through, then I would start asking, let me say. Okay, so for Carcará, since you have focused on the air vehicle design to some extent, and you have come up with an innovative propulsion configuration layout, and I found it interesting, and I would like to ask you, because the rationale seems to be mostly based on stationary conditions. So what about transient, when you are to transition from one mode to the other? Have you considered that, and what were your findings?
Thank you for the question. Actually, we did an effective calculated the transition part mostly because of the time we have to develop the project, but we think about some solutions. So for the tracing to the horizontal flight to the hover, maybe a PID controller will be a solution to be developed. So it can modulate the thrust between the two motors. The hover phase to the horizontal flight again is something that we call the thrust switch maneuver. And the solution we thought for that is to hover at a higher altitude than the normal mission, and then we can switch the motor configuration so that the aircraft will descend and lose altitude and then accelerate, and then we can again modulate the motor's thrust to go to the horizontal flight phase again.
Okay, so you would allow some altitude loss. However, you should think that during this altitude loss, should that be acceptable, you cannot lose control of the air vehicle. Otherwise, even if you allowed some screen height, that's just the tip. When you consider unconventional solutions, the devil lies in the details. So just keep that in mind.
Yeah, we know that our solution was innovative. That was something that we wished, but unfortunately, and we also know that the best way to design an aircraft is to feedback all the time the design with practical tests. But unfortunately we couldn't do all the tests we wanted to. So that's a matter of time of developing the project and also resources. So that's what we came to.
That's great. You're bold, and I'm just putting some thoughts on your mind. It's not a critic, okay? So it's good.
Thank you.
Thanks. So I must also start by saying that I'm impressed. I really enjoyed reading the 3 reports. And I even more enjoyed your presentation, because that also, a lot of the questions that I wrote when I read the reports, actually you explained during the presentation. So, but there are still some. And I also was really inspired by the broadness of the project and how you have focused on different tasks, as we just, and imagine if we can combine the knowledge and all this into some big projects. That would be great. Yes, so then I can start by asking the University of Sao Paulo. I mean, it was a really interesting presentation, and I really enjoyed your background research, the discussion with the fire department and how fires are treated in reality. And I really like this, that you had many practical aspects of your project and discussed fire resistance and these things as well. One thing that I would ask you is if you had any thoughts on the redundancy. I guess that the separation or the ejection of the drones from the KC aircraft is a quite risky process with the parachutes and boxes and all these things. And I guess in a real situation, there is a high risk that some of the drones, maybe even the master drone, get sort of injured during this operation. And what are your thoughts concerning this?
So first, we have the box, the case. There is a protection for the drones to avoid any damage to the structure. And the box would be projected for standing the dynamic of the air, the impact of the parachute opening. We haven't have the opportunity to make these calculations for the box, but our ideal box would support all these effects. And And about the master drone, I will pass for him.
Okay, so as explained by our presentation, we use one master drone. So what could happen if this specific drone like fail, right? So this was mentioned also because it's a future work, but we know that in the aircraft field it's very important this kind of redundant systems. So yes, we didn't perform this redundant system, but the future work, and we know that we have some this weakness in the system, but we can solve this in the future.
Just to add one more thing, in our approach, we choose to have this master drone as just as another drone, because using the central node outside the drones, we could just as a simple solution have other drone take the the part as the master drone. We could lost a little of combat fire because we've lost drones, a number of drones to combat it, but a simple solution would be something like that.
Yeah, thank you. I agree. I also think that would be a good solution in this situation. Thanks a lot.
Okay, yeah. Thank you all very much for your presentations. Very inspiring, and I just concur with the other speakers. So I will ask a question to São Carlos. Santa Catarina, sorry, SC. Yeah. So what kind of avoidance for collision did you integrate in your system? It looked a bit on the simulation like they flew onto each other. Was there a control of this, or?
No, this part is managed by MRS UAV system, which is the framework that we built upon. But avoiding collisions, this is all part of the MRS UAV core. So when one drone starts nearing another, it automatically stops its trajectory to wait for the drone to clear the airspace. So this is all part of the MRS UAV system.
Okay.
We didn't alter it.
Okay.
It was already made.
Then I have one question for all three contestants. Did either of you consider communication aspects? I guess it's some kind of radio communication, bandwidth, the need for bandwidth,
Yeah. So first, our group did a small communication that is broadcasting the fire position, but we didn't really analyze on how this would be implemented, on how the communication would be dealt. But we still have a lot to work on. Multi-agent systems, really, they have to work on collaboration. And so far, we have a demo that shows a little bit about that. But for a multi-agent system to be really taken in place, it has to be more than that. It has to have more communication. But this is for our team.
So we didn't consider bandwidth constraints also. Well, for the simulations, we just assumed communication was working all the time. We tried, but it was a more complex problem than we thought. Like proposing a control law to guarantee a minimum bandwidth. It was too complex.
Since we use the simulation, we just consider that we have a good communication between them. We didn't consider using, we didn't thought about bandwidths or anything like that. We talk about something like if you could use radio frequency or some type of 3G or 4G, but since we're in the simulation, we have a central drone communicating with all of them. In the simulation, we just assume that we got okay communication between them.
Okay, thank you all.
Okay, thank you very much for the great presentation. Great jobs for all teams. So I'd like to ask to all the teams, what's the autonomy of your drones? What is the expected distance from the dropping of drones from the KC to the area where the fire will be located? And what is the distance from the area where the fire is being located and the final area where the drones will be sent to the end of the simulation?
So the autonomy that was calculated was without the payload, we have like 13 minutes, nearly to 30 minutes, and with the payload, 1 kilo payload, we have 6.5 minutes, nearly.
In the simulation, the total simulation time was a little bigger than this, but with the real-time factor that calculates the real time of the simulation, real life, it was 6 minutes and 30, so it was really close to the calculated value, and with the distance between the drop and where the drones would land, we have considered that the drones would follow in the center of the map, as it was in the simulation provided by SARC, and the distance of the map, we considered the values of the gazebo, that was 200 meters for 200 meters, and the base location, as it was said in the digital, the requirements of the project, it was a known position, so we set the position of the simulator to a specific location, and then the drones would be sent to this location, because in real life the base location would be known. And the distance would be approximately 100 meters from the
Yeah, because if the drones were launched far from the place where the fire should be located, you don't have enough time to accomplish the mission, to extinguish the fire. That's the question.
Yeah, one thing that we consider just when we, like in a real situation, if we would use this approach, we'll first, of course, have map area for something like Google Maps or something, so you could like measure where would be the drop location and the rescue location, so we could have a little more time in the real-time drones to deal with it, we think.
And one more thing, that in the first stage of this competition, we tried to make a self-drone, but we couldn't really get real results. But our stipulations for the autonomy was nearly to 18 minutes. Of course, we need much more money to invest in batteries and motors that could afford this autonomy. So this wasn't a thing we could really show that was possible. But that's, by calculation, this was our objective.
Okay.
Thank you. We calculated the endurance with a method proposed by, I guess name is Traub. The author of the paper is like a Brigade equation for battery-powered aircraft. And I guess it was 23 minutes, the endurance. It was enough to meet the requirement of the competition. And so that it was. So we couldn't test that because We couldn't buy the motors and the batteries to test, but that was the theoretical value of our endurance.
With respect to the drone's height, when we tested dropping from the KC, the detection system would work consistently with the drones flying for 50 meters, about 50 meters, which is actually an advantage to the path generation approach we took, because it considers the range of sight to the ground, and when the drone is higher, the range is bigger, then the path is minimized.
So, as I mentioned, we are still on the final processes of recovering the SK450 that we worked on previously. So, we still haven't tested this drone on dropping the payload. The height that we can inform you is the height that Menegal made on the test, which was around 10 meters, but that's it so far. We're still in the process of recovering our drones and maybe detecting problems, and let's see if we have to acquire a new one. Still unsure about that.
Okay, thank you.
First of all, I would like to congratulate all teams. It's a great job considering the time that you have to do this job. I have several questions, so let me do something. I have some questions to Carcará. How do you expect to control the roll attitude of the aircraft, considering that you have only 2 motors to control the attitude of aircraft?
Okay, we know this would be a problem. The aircraft can really be controlled when it's hover mode, but we did some preliminary calculations regarding using some wind data, and we found that for approximately 95% of the wind gusts, we took the data from Belo Horizonte, which is our city. For approximately 95% of the winds, it doesn't create a disturbance enough to affect the performance of the mission, but if in case of those 5%, or if there is a wind gust that is a little bit harsher, it can always go to the maneuver to transition into horizontal flight. But it wasn't our idea to be controllable in the hover flight, just to meet the 5 seconds requirement. This is like a short time.
Okay, and why the team decided to use a rudder? Since the mission requires a very simple aircraft, and the rudder is more used for quality of flight, not for low cost. So why to use a rudder?
We try to integrate with the trajectory prediction, and we wanted to make sure that we couldn't really simulate our geometry and in the simulation, because it's quite a different one. So we wanted to make sure that the trajectory was possible in our configuration. So we just added it, since we would have the winglet anyways to provide the stability. We just wanted to have some type of control, just directional control if needed to perform all the trajectory.
Okay, I saw the envelope of loads, and you consider 34 meters per second. Why do not use 85 meters per second, since this is the real load?
Sorry, I didn't understand the velocity.
In the project, you consider the load envelope of 34 meters per second.
34.
But the real situation is 85 meters per second, because this is released from an aircraft flying at 85 meters per second. Why do not use 85 and use 34?
We didn't expect to operate in this velocity of 85 meters per second in the horizontal flight mode. Our interpretation is that the
aircraft will drop the UAVs in the hover mode. So when they do this part of the mission.
Okay.
And the motors, they aren't even able to provide such velocity, so we just calculated with what will be the operation. The idea is that it will be dropped from this velocity, but then it will eventually decelerate, and we would operate on the velocity that our motors would provide.
Okay. And I not see anything about the mission controller. Could you explain better if the mission controller is centralized, distributed, and the main functions of mission controller?
Sorry, if the mission controller is...
The aircraft that manage the fleet. The aircraft that send the commands to our fleet. Swarm or all drones. I read the report and I did not see anything about that. How to control the fleet, if there is a centralized controller or if it's a distributor controller, and how to do that.
No, we don't have a centralized controller. Actually, each drone will react to the other's information that will be sent constantly all the time of the mission. Every drone will receive data from position and vision from other drones so that they can position itself with regarding each other and get the information of the fire location.
Okay. I have time to more questions. Sorry? I have time for more questions? Okay.
I'm sorry, just to interrupt you, it's a little bit too low, the volume. Maybe if I could repeat your questions, just that you know that I will repeat your question. Because of the sound, we're not able to.
I have one general question here, so, and this question would be if the teams consider in the algorithm of the prioritization on defining the first point of fire to be attacked by the team, by the swarm, because I understand the swarm has a main goal to finalize, to overcome the fire problem. So if you have in your algorithm this kind of idea on how to prioritize the first point of attacking the fire, the problem that you are facing, that condition. So this is the main question for the three teams. I have some questions that the other juries already addressed to the team, so I will not repeat here. And specifically for the last team from Santa Catarina, I would like to ask about the discussion you have two kinds of methods, the decentralization and the cooperation. So I think they are a little bit against one another. So how the decentralization and cooperation will work? Because in one point you say that the drones will have autonomy to work, and in the other point you say they will cooperate around one main objective. So this is the main questions that I have. Thank you very much.
The groups, do you understood the first question, or should I repeat? The first question was related to how you prioritize the point of fire to reach the goal for firefighting? That was the first question, and the second was direct to Santa Catarina.
So in our proposal, we don't have a really prioritization of which fire to go first. We basically work on whichever agent finds the fire first, broadcast it to the other agents, and then they go attend to this fire. So basically it's a first come, first served idea. So Glauco, should I answer the two questions now, or do I go? Okay. So the question about decentralization and cooperation. Decentralization, basically what I said is because each agent is running on that code. So there is no master agent that is commanding the others. So all agents' code is basically the same. They all have their actions that they can pursue themselves, but they do work in cooperation because they do broadcast their beliefs, their perceptions of the world to the other agents. So each agent has its own beliefs, but it can tell the others what it's perceiving around him, so that the other agents can do with these beliefs, can then decide what goals they are going to do with these beliefs that are added by communication with other agents. So there is no main code. All agents have the same code, and they all have they are independent to act on their own.
In this regard, our approach were pretty similar to Santa Catarina teams. The first robot to identify the fire will send the position of the fire located to the others, and they will enter formation based on that first site. But once the fire is extinguished, they will return to the predefined point of collect.
Okay, we didn't implement a decision making of where to focus if we have more than one fire spot, but we can. I think the best approach will be considering the autonomy of the other drones. So the distance between them, if we have the different fire focus, and we can make a decision considering the autonomy to focus in only one fire spot.
Go ahead.
Okay, so may I do the question now?
Yeah. Go ahead.
From the USP team, I also was curious about the release mechanism that you had with the magnetic field, and you were concerned about the autonomy and the time you have to fly with your UAV. And the solution was to maintain an electric field, electromagnetic field, and once it is in the point, you just release by interrupting the electromagnetic field. So I would like to ask you if it would not be the opposite idea to have a more autonomy. Did you took that in consideration to have another system using the electricity of your UAV, since you have the problem or the concern on autonomy?
In our paper, we showed some calculations on which current was the most optimal for making the field hold the payload, and we've come to some numbers that didn't compromise the autonomy of the drone in the long range.
Okay. Oh, good. So, well, I think we have many questions, so I'll try to summarize several of my questions into one that is applicable to all three groups. I'll try to do that. So, and I'll try to pick up from previous questions made by my colleagues here. So, regarding, for instance, have you considered communication performance issues or air vehicle performance and endurance that you have left? And, for instance, UFMG Carcará team have designed the air vehicle and use as objective function to minimize the empty weight, with the arguing that this strategy would leave more room for useful load so that you can use that as fire retardant and fire extinguisher and so on. And the other teams, USP and UFSC, you have selected commercial off-the-shelf platforms and use that into your solution and try to derive some concept of operation, how to extinguish or accomplish the mission using them. But what I've missed, and I would ask all three of you, because the complete solution for when you're given a problem like this is the technical solution from the platform, sensors, communication, and payload, and everything combined to a concept of operational, how you are going to, you intend to perform. And since you're considering all swarms, some of you have selected some swarm sizes, indicating that it's optimized to cover the area, but the pattern you've used, it's, well, you haven't really detailed how you come up with that number of swarm, at the size of the swarm and the pattern that you're going to use. So my question is, how have you considered the solution performance or the vehicle combined performance so that you can actually see, well, am I meeting having a mission effective solution? Because I will try to avoid, for instance, some of you have the simulation environment with a nice graphics visualization, and I would argue that you should try to avoid having a false sense of fidelity because you have nice graphical visualizations, and you always try to make sure that you have the physics behind it, otherwise it's giving a false sense of, well, it's simulating and it's working, but the air vehicle performance, the sensors, the platform, everything. So I would like to each of you to describe briefly how have you considered the actual mission performance and how do you see that, well, my solution is accomplishing that, or what missing things that we would rather prefer to work if you had more time available.
So first, I think we could, each of us, like add other things, because I'm not expert, for example, in electronics or mechanics. But talking about, for example, the number of drones or something like that, we didn't do a lot of research on the number of drones or what's the best way to use our idea of swarm with a main drone, etc., with this number of drones or this type of sensor and stuff. Okay, sorry. So the number we end up was just thinking about, okay, we have a main drone, we have an area that you should cover in a small amount of time and have a little time to fight the fire, because as we talked about with firefighters, we know that the fire spread is very quickly, so we're thinking about raising the number of drones, but at the same time, with more drones, the control is much more complex, and because of the only way that you could see if our option was at least a little viable is through the simulation, and due to problems with, not problems, but with limitations with computers, we saw that the number of 9, for example, was like the higher that we could get, having an okay simulation, having a way to test everything that we're thinking of. So the idea of this size of the swarm or the approach with sensors was a little limited by the way that we could show and could test if our idea was viable.
On the mechanical part, we have a really hard limitation on available of materials and cost of materials. We couldn't go into something very costly because it's out of our reality, and we couldn't go to materials that aren't available for the general public. Sorry, this would go too long to explain. But there are some materials that we researched, but they aren't available for the community as general to implement them, to study them, and are new materials, and we have like these hard limitations. And we try to bring the solutions under the limitations that we have, respecting the limitations of the competition. The 5 kilogram takeoff mass, the 0.5 cubic meters, and others.
Just a comment here. When you have budget limitations or things like that, one thing you could do in your report, for instance, you could try to think about a solution that complies with all the requirements and the rules and everything else. And you can think, wow, it would be too expensive for the demonstrator we are intended to build. Okay, so you can simplify the demonstration and the demonstrator and say, oh, this is a proof of concept and we are going to demonstrate just this piece of the solution. But you think, or at least you convey in your report, well, my solution is not complete mission effective because I have this limitation. So it's important for you to state that, those constraints, and that's my...
I think Miguel said in the first half of the competition we did something like that. We went for the ideal specifications that met requirements, like autonomy was much higher, and for the second half we chose a more realistic approach so that we could do demonstration better. Something like what you just said.
Regarding the drone swarm size, we thought on the availability of the drones to complete the mission. Based on that, it's possible that depending on the size of the fire and the size of the range of action of one drone, for example, he wouldn't be able to accomplish that. But our approach for targeting fire was based on if I have the number of robots that the sum of the range of action can cover the whole fire simultaneously, they will enter in a formation to accomplish that without having exceeding range of action being not utilized because it's out of the size of the fire. Regarding the feasibility of the mission, we, in the MRS system, there was some overshoots, there was some kinds of moments that the drone couldn't quite accomplish the target, the trajectory, and we run a host bag, a log of all the velocities sent by the vector field in the position during the mission, and with a controller for the two stages, two modes of flight, one that is planar, it's from a plane like, and we only have to worry with the EL velocity and the linear velocity, and comparing with the limits of operation of the designer aircraft, there would be some points of which there will be similar occurrences as the drone in the simulation. There will be the overshoot, some sharp turns might not be done perfectly, but those occurrences were, we have data to assume that they wouldn't be critical to the mission, even though the trajectories wouldn't be perfectly followed in some occasions.
So you asked what we could do in the future if we had more time, and regarding communication, we did read about consensus, and we thought about using that consensus in multi-agent systems, but we didn't apply it because we considered we wouldn't have time, because we didn't have a plug-and-play library just use. We would need to first understand the whole theory and how we could apply that to our project. But that is a path I think that could be nice to follow.
Yeah. First, you mentioned performance tuning of the simulation. So performance is a very delicate aspect of multi-agent systems implementation. Historically, multi-agent systems have proven to be more about research and less about implementations. So as I mentioned, our simulation, that's what motivated us to do the JSON-ROS interface, to move towards a more implementation side of multi-agent systems. I think recently we also had the Morai simulator, not for drones, but for machine learning of autonomous vehicles, where the multi-agents were responsible for controlling the pedestrians. But yes, so far our simulation is still needs to be tuned towards more performance, and this is one of the things that motivated us to participate on this event. You also mentioned how we chose the drone model. We basically just chose what we had in stock, which were the drone we had on the proven project on the side of Santa Catarina. But ideally, we would move towards using the drone that is currently being developed by Provant. The more responsible part of this is on the Minas Gerais campus, which is currently finalizing the steps of developing the Provant 4.0, that is a VTOL drone. You also mentioned how we chose the mount of the swarm. Basically, we chose the minimum that we could implement. As I mentioned, our trajectory calculation basically so far has to be a multiple of 2, so a binary number. So we chose, as the minimum was 5, we put it at 6. But the quantity of drones are easily modified. As I said, one of the advantages of the multi-agent system is that it offers high scalability. So with some changes on the coordination, we could improve it. As I mentioned too, we tested it with 12. We could increase it further to check if the simulation stands.
Okay, so just to wrap up here, you've mentioned that you would have capability to implement that in the simulation, and I'm just saying that for all of you to consider in your simulation not only this kinematics of the simulation, but also consider, for instance, if you could track battery state of charge or performance parameters for each drone in a swarm, for instance, consider, and this is one question that was raised before already, if you have multiple fire spots and you have to have some logic to fight those separately, and consider that, well, you have broadcast, well, I've detected a fire and call for the drones, but then there is a drone that has just fought another fire and its battery state of charge is low, but it's meeting your criteria to engage that other fire, but it doesn't really have the performance to do so. It would have to return to base. And then with all this combined, you can really think in a given scenario, what number of drones do I need? And what level of performance do I need from each of them? And maybe more is not better. Maybe you have to have more capable but less numbers, or the other way around. And that's part of the whole solution. So that's just the thinking I'm trying to bring you here, that it shouldn't be sized by simulation limitations, although I understand it is something that you have to consider because you have to perform and to simulate and so on, but you shouldn't be bounded to that for the actual solution. Okay? Well, thank you very much.
Thanks. I have as well a question. I have many questions, but I have to limit myself, of course. I'm very curious about your projects. But I have one comment or question to Karkara regarding the design. I really like this aircraft design aspect of your work, and I am also a fan of blended wing bodies, so I really like your design and layout and so on. Although I agree with one of my colleagues that maybe removing the rudder will be a good idea to simplify the design and gain weight and so on, or gain weight for water or other things. But my question is that you have applied this FAR requirement on the normal acceleration and so on, and I would like you to comment a little bit about what do you think about the applicability of that type of requirement for a vehicle like this, working in this quite harsh dynamic environment with separation from aircraft and fires and so on?
Sorry, we didn't understand very well the question. Can you repeat, please?
Okay, my question was that for the design of the structure, you applied like this FIR requirement developed for like commercial airplanes on the loads for designing the structure. And my question was if you can comment on the applicability of such a requirement on a vehicle like this in working in this type of environment.
Oh, okay. Actually, we used this regulation because we didn't have access to another one, but once we had a lighter craft or a craft that actually do a mission that can be similar to an aircraft that fits this regulation, we decided to use it because of lack of options, really. We didn't know another regulation that we can fit our aircraft in and to calculate the loads diagram.
I see. Thanks. I agree with you. I guess there are no good regulations to read in designing this type of vehicles, of course, but I would guess that this platform will be subjected to much higher loads than what is actually required from a regulation like this. So I guess an experimental approach would, for instance, be quite good. Could work in this case.
Yeah, I think the best solution will be if we could really fly our craft and made some measurements with sensors, like an accelerometer or something to calculate the load factors, the actual velocities, but we couldn't do that. But I agree with you that some experimental tests will be ideal in this case.
Yeah, I guess you can even try one and see if it breaks, then you make it stronger, or something like that.
Yeah.
Yeah. Thanks for the answer. Good. And I have one question for the team from Santa Catarina as well, and that was like a more general question. And it's like, what is the biggest learning from the project? The most important lessons learned overall in this work.
Well, as I mentioned, what we took more of the project is that multi-agent systems were they are very interesting on what type of problems they can be more interesting to use, such as problems where an agent cannot perceive all of the area, but we did take it away that so far it's rather research focused, and what we took from it is that we need to improve multi-agent real life applications so that this area can be more represented on real life applications and commodities and so forth.
Thanks.
I have one more comment on the loads. I think I agree that the loads are probably much too low here, but as I'm thinking an idea would be to perhaps talk to a experienced model aircraft builder and compare with the weights that you have and so on, to just give an idea of how to size the things. I have one question also about the engines. I didn't quite understand the airflow in the engine. Normally the air comes from the front through the engine and it sort of makes extra speed of the air. Where does the air enter into the engine? I didn't understand that on the illustration.
Maybe the drawing is not clear enough, but there's a hole in the fuselage, so the air comes in in tractor mode and then gets out at the end of the fuselage, and the rear motor works the same way. So actually there's a hole on the fuselage. Maybe the drawing we couldn't see exactly that, but that's how it should work.
So when it's flying in flight mode, the air enters in the front of the aircraft, and then or in the nose, or
in the nose motor it enters in the front, and in the rear motor it enters in back.
Okay, I didn't quite understand. Have this kind of concept ever been used anywhere ever?
No, that we know. Actually, do something innovative is something that we wish to, as I have said.
Yeah.
So we haven't noted any aircraft that use this system, but we really like to try it. We couldn't try this experimentally, but a test we were planning to do is to make a system that can balance. I don't know how to say. It can balance. A system for the motors to balance with a controller, but we couldn't develop it due to the lack of resources.
Okay. Interesting. Oh, I have one other question. How much fire can you put out? I think it's a question for Sao Paulo, who visited the firefighters. This fire retardant, how much fire can you actually put out with 1 liter of fire retardant?
And so when we were talking with the firefighters, they said that 1 liter is not very effective. It should be thrown in the middle of the fire. But when you make, they called the fire breakers, we stop the fire from spreading, making that the fire kills itself.
Okay.
Because it's nearly impossible to try, unless you dump tons of water in the fire, you can't stop it by human effort. So the objective is to wait until it's decreasing intensity, because just like the firefighter said, they can't do anything unless wait.
Yeah, but but do you think is it like 1 square meter or like 10 square meters? You can spread this liter over to. I'm just thinking of the circle you did with the aircraft,
Oh.
and how long does it take to release this? When you use the electromagnet, you release it. For how long does it take? Will it just splash down there, and then it maybe will only be over, like, I don't know, spread over a very small area, or?
So our release mechanism, it was kind of theoretical, but it would spread, releasing here to spread over continuously until the 1 liter is. We didn't calculate like a number of meters that this would effectively use. It's like
It would open a valve and then it will pour out. Yeah.
Yeah.
Okay. Yeah, I see. Okay.
Thank you.
Thanks.
Based on the last question, I wonder if it will be good to evaluate the size of the fire before to send the drones, because if you have a huge fire, big area, it will be useless to send the drones to that area because it will not be possible to extinguish the fire. Did you consider this in your simulation? How do you calculate the number of drones that would be necessary to extinguish the fire in the forest?
Well, as I said for his question, we didn't consider the area of fire or anything to measure the number of drones to it. But as we talked with the firefighters, the time of the spreading of the fire was very high. So even if a small fire in the forest would take a little time just to be out of chaos. So the idea of the number, as I said, was just due to simulations and limitations, but we didn't consider the area or something like that to be something to just not do the approach or something like that.
It's also, there is the behavior of the fire. That's it's in our mission was a little rudimentary. I don't know if it's the right word, because you're saying that we are making a like circle the fire, but the behavior of fire is not exactly like this. And to implement the right procedure to show the fire, the real fire, would be needing more study, because there's no need. Why they talk to the firefighters? It's not, the fire doesn't spread all directions. It's come by, depending on the wind, they go into a direction. So we need to study this, and so like our procedures are a little rudimentary and basic.
I believe it would be good if in the simulation you calculate the probability of extinguishing the fire based on the size of the fire. So adopting this procedure, you can prioritize the areas where the drones should be sent to extinguish the fire based on the capacity of the drones and the amount of the liquid of the fire extinguisher. I think so. If you could.
We didn't consider the fire area before dropping the drones, but we take it into account when calculating the maneuver, the formation the drones take when they do the maneuver. Our approach is based on a paper from the University of Lancaster, where he proposed an hexagonal packing, and he proves this is the best formation to avoid congestion. And so if the area information is given by the bounding box we calculate in the vision. So we project every vertex of the bounding box on the ground, and we calculate the diagonal of that rectangle, and the path, the formation algorithm distributes the drone based on that area. This is where we show an example where the drones are like in a straight line, and then in the second example they are in a triangle formation. It is based on the fire area.
So yeah, initially we aimed to use the camera, the color camera, in addition to a proximity camera that is available to attach to the drones used on simulation. So initially we had the idea of using the camera to detect the red tonality, so to detect fire, and the proximity camera together to do object detection, and from that calculate the area of the fire. But that proved to be more complex than we thought. So far we assume that the fire area is the fire area of the one tree on the SARC environment, and apply that to that. So.
Okay, let's talk with the USP guys. I would like to know why the team decided to use parachute and not let the drone fall down.
Sorry. And so first, the parachute is for slowing down, so we can activate the free fall mode, because the 100 meter per second velocity is very fast. Like, it's really fast for the structure, the air vortexes, the impact of the structure. So we need to slow down before the drone can start to stabilizing. Because in really high velocities, the propellers stall, and we wouldn't have like anything to stabilize. So we think first on the parachute. Then we started to think on the parachute on the structure of the drone. This brings the problem that the parachute would impact the structure with, when it opens, the forces would be higher than the yield limits, and bring all these problems, and the impact of the air vortexes, and the other effects generated by the KC would really impact the structure, the components, and we could end up compromising some of the drones. Then comes the idea of the box to protect the drone. And it's like this progression that we are on.
I want to express more this question, because you know that if you open a parachute, normally we will have a 4G impact, 7G impact, or up to 9G impact. And it depends on the type of parachute. For example, if you have a acceleration reduction of opening of the parachute system, you can reduce this number of Gs. For example, on a parachute that has no system that reduces the opening of the parachute, the impact of the opening is 9G. So it's I believe that's much more if you compare with the let the drone fall without any system. So on the other hand, if you put some system to reduce the opening of the parachute, the system becomes too complex. So I believe that if you test it, you change your opinion.
Well, we haven't tested, so I can't argue with that. However, the box would receive this impact. This is our ideal box that would absorb the impact for the drone to can be open at a lower speed with much more stabilized condition for it to enter the free fall mode. And the box, it's like our card on the hand, like our ace of spades. And the box would receive this impact, the box would receive the 9G from the parachute, not the drone.
Okay, and another question. The solution to deploy the fire retardant only over the, let me say, not in the center area, but stop the propagation of the firing, requires that you have a very precisely putting of the retardant. So do you calculate the wind action of the retardant? For example, if you deploy the retardant system, I don't know if it's a ball or if it's a aerodynamic format. It has a aerodynamic format, but do you consider the wind in this calculation? For example, I should deploy in this position to get the right coordinate of the fire.
And this part of the project was not yet finished. It is also in our further improvements points that this is still a working process. So we haven't considered this yet, focus on the yet, but it's something that we can go forward, we can make the calculations can validate it, this point. It's a very good point. Thank
It's
you.
very important because if you have a very high temperatures local, you generate a wind in this region, so you should estimate the wind flow to deliver the right position to deliver the fire retardant. And the final question: why do you use only 9 drones? Why do not consider more if you are using a 2 low-cost drone?
Well, as I said, we have a little limitations on the simulation, but as we all discussed, we could just simulate it with 9 and theorize what we could do with more. We didn't take into account like the budget that we had with like the budget that the drone costs to have like a speculation of how much. But
why the magic number 9? because I did not see anything about the fire retardant specification in any team. But for example, if I deliver 1 liter, how much area the fire retardant sting the fire? So if I have, for example, in medium, I don't know, maybe 100 square meter, how to solve this problem? I will need 10 drones, 100 drones, 1,000 drones. This is very important to solve the problem. I saw that the teams work on the solution, but not the customer solution. The technical solution, but not the customer solution. The customer solution is how to solve the problem. I have 100 meter, 1,000 meter square to solve the fire problem, and how much drones I will need.
Okay, the number of the drones considered was estimated based on the size of the fire provided by SARC in the simulation environment. And from the conversation with the firefighters, we have concluded that for a bigger fire area, it would be more effective that the firefighter act with the drones, and the drones served as a support for the firefighters. Because with a fire area too big, it would be probably impossible to seize the fire with only drones. And if we make the number of drones too high, it would be the cost would be too expensive and probably not worth it.
Brigadeiro Falador, do you have additional questions or comments for the groups? Okay. I think, is there any other question? May I give the word for our co-chair here?
Thank you. I have a question for all teams, and this is not about the work that you have done. So I'm the teacher head over here. I want to see how you guys think and reason on this question for all of you. Let's assume that 9 drones plus the controller, 30 drones was you guys. You, I don't remember, how many did you have? 6 with or without controller? 6 independent or 6 with a mothership? Okay. Let's assume every single one of these is a unit. How many units can you put in your KNC 390? Did anybody actually make the estimation out of volume? That's the first question. The second question is, how do you actually run the operations? Were you planning on having each one fully loaded and the airplane fully loaded at all times? Do you have to load the plane? How long is it going to take to load the plane? Because you guys talked about taking the idea from the Americans of dropping things with the parachute. How long is it going to take for you to load one plane? And what's the impact on the fire afterwards? The Canadair can be up in no time. Big lake, lots of water, fast. How long is it going to take for you guys to be actually operational from the get-go of there's a fire?
So yeah, that was a point that we did not exactly take into consideration. Regarding the KC cargo, we based that off the model that was offered by SARC. So we did have to do some adjustments because on how it spawns, it has a radius inside the KC, but the cargo of the KC would impact on the drop processes, at least if it was meant to be using the MRS UAV system, because it does affect on the collision detection between drones. So yeah, that would have to be taken into consideration. But it was something that we just established the number 6. We adjusted the cargo inside the KC, and it worked. So we didn't plan any further onto that. On one unit of KC. Yeah.
Okay, so as we presented our estimation, we designed the drones especially to fit as many as we could inside the cargo space. So we got to this number 30, which would be the maximum capacity. And about the approach, we didn't think thoroughly about that, but I believe the best approach would be to have them all fully loaded and have the KC fully loaded as well. And just to, if we can have information beforehand about the fire, then we get it fully loaded. And if we arrive there and realize a small fire, then we don't need to implement all the UAVs.
Well, we didn't consider like the size of the KC for putting a lot of drones there, because it would be actually more efficiently having more drones inside a higher space. But in the beginning of our project, we were talking with firefighters. The first thing we thought that the time to have all the drones ready to go there would be almost the time of some group of firefighters going there. So at the beginning, we already know that it would be the main problem of it, because even though we create a huge, perfect approach to destroy the fire, with the time to be just to consider getting all the drones ready and putting all the drones in the air, having your central base ready and stuff would be almost, if there's no firefighters there, would be just an enormous chaos, and the fire would be impossible to stop. So in the beginning, we already know that would be a huge problem, and in fact, we don't have like any measurement of the time or something like that to answer your question.
All right, thank you very much. Those are good answers. All projects are very interesting. Still being the teacher, I'm going to give you homework. It's your own doing. You all left yourself with future work slide. Congratulations on getting more homework. Go figure this out. Because if this is an idea that is going, and this is an idea that we're seeing more and more, both at research level, at the engineering level, because just an example, a few days ago, 2 Italian pilots crashed trying to put a fire out. So the idea is important, and there's a lot of work that can be done. Try to figure out how you're going to operate this, and how much is it going to cost to keep one KC-390 fully loaded at all time. That will make all of your cases basically unattackable from all sides. Congratulations.
Thank you. Thank you. Before closing this session, I would like very much to thank the jury board for the excellent questions. I forgot to mention, thanks very much, colleagues from ITA, for being here. Professor Emilia, Solange, Gil, it's an honor to have you here. Without you, there would be no competition. Also, thanks to Professor Simini and Professor Vitor. They really helped us to bring this here to a concrete competition. Thank you very, very much. And also CISB, Alessandra just went a little bit out, but CISB also helped us a lot. Just for organization purposes here, we are a little bit late just to catch up with the schedule. Just to confirm, you were going to do some exhibition or some, it's cancelled? Oh, okay, no, not exactly now. That's just how much time you need to put Okay, okay. Just that I can grab some food for the jury board so that we can go through lunch. Are you going to show something or? Okay, okay. Anyway, the jury board will have time for lunch, and then we can confirm if you're going to show something. I'm going to also to thank Brigadeiro Folador for being remotely with us until now, and we are coming back for the jury meetings. They are going together in a private meeting. And thank you very much. We conclude here this oral presentation. Thank you very much.